I like to have fun too, especially in my talks, and especially with the audience. So what I always say to my audiences is, please do ask me questions during the presentation. If you don't ask me any questions, I am going to ask you some questions, and I've had time to think about this, right? You have been warned. So what I'm going to show you about is some work that we've been doing over the last few years. Go ahead.
How much time have you had to think about this?
Most of my life. Since I did a PhD. So what I'm going to show you about is some work we've been doing over the last few years, funded by various bodies, including the European Union and particularly Scottish Enterprise. So what we're trying to do is to take some research work and we're trying to make it more practical. We're trying to bring it into the real world. So I'm going to tell you about something about how we're going to do that. So let me start by motivating the problem. So Multicore is now ubiquitous. I don't need to tell you this. Even this little laptop, which is sitting down here giving the presentation, this is a multi-core machine. So how many cores does my laptop have? So you weren't quick enough with the questions. How many cores do I have in my laptop? Volunteer. 2, oh, you changed your mind. 4? Any advance one? Any 2? Who thinks 2? 4? More than 4? 16? 32? No, it's Apple. But, well, let me tell you. So let's work this out. Well, I've got 2 x86 CPU cores. That's a pretty good guess. But maybe you've got hyperthreading, so maybe there are 4 rather than 2. What do I mean by a core? What is a core? Okay, philosophy question. Oh, I've got 12 GPU execution units. Okay, we don't normally think of those as being cores, but I'm pretty sure they're processors of some type, aren't they? So there are 12 of those. A bit restricted, but they're definitely cores. Oh, I've got 2 HD video encoders, decoders. These are cores too. I have a Bluetooth controller. So there's a little device which is sitting in there, just speaking to my phone or to my pointer thing and keep maintaining the connections. That's a core too. I've got a disk controller, just speaking to the disk. I've got a power management unit. And the power management unit, its job is very simple. It's just sitting there in this laptop. It's waiting for me to press a key. It's trying to keep the device running efficiently. And that little power management unit is more powerful than the very first processor that I ever programmed, which happened to be a 6502 way back when. So in total, we've got some 20 or more cores. Not all of them conventional CPU cores, but they're all processors of some type. ARM apparently is very proud of the fact that it has more cores in a Mac than Intel does. Where are we now? Well, where we are now is moving into a brave new world from these multi-core devices, which have started to take over the landscape, towards much more powerful devices, things like this one that was released in September, the Intel Xeon Phi 7920. This has 72 x86 processor cores in a single package. Phenomenal device. Anyone notice any interesting features about this? Clocked quite low, yeah. Good observation. 1.5 gigahertz. Do they even make processors that slow anymore? I guess so. Anything else? Well, 260 watts. That's quite a lot of juice. I wouldn't want that in my laptop. It'd be a little on the warm side. There's a compromise going on between the core speed and the amount of power that devices are consuming. And this is driving the future of computing. roughly speaking, we can have more processors for the same energy input, provided we make them run slower. Come back to the point later on. You'll also be pleased to see, go ahead.
Wouldn't the heat be insecure?
Possibly, you're saying, if you can see. Let's try that. Bit of feedback. So if you could measure the heat coming off a processor, could you figure out what it was doing?
Yeah.
And possibly you could, but then if I was really worried about things like that, I could always, for example, just run a background computation that always did something, right? And then you wouldn't be able to tell. So if that was the real issue, if it was the real issue, you could do that. Yeah. So that's single chip. This is Intel's most powerful device ever, and if you're in the market for a MacBook Pro, you'll see it's a bargain at only $6,000 odd. So go out and buy a few. Where are we going? Well, we can confidently predict that we're heading towards a future where we don't just have tens of cores on a processor, but we have hundreds, we have thousands, maybe thinking way ahead, we even have millions of cores on a chip. I'm calling this the megacore computer. You can check it on Wikipedia. I was in Budapest a few weeks ago. There's a Wikipedia editor there, and he promised me he'd try and get this name attributed to me. So it's going to be my claim to fame, apart from doing some stuff with Haskell. What are these things going to look like? Well, they're going to have nodes linked into systems. Each of the nodes you can predict is going to have several large CPU cores, plus probably some specialist accelerators, so highly heterogeneous probably. High-performance network linking the nodes, and probably not much memory per core, because the memory you just cannot scale in the same way that you can scale the processor technology. So memory is going to become much more limited relative to the number of cores that we have, probably. We're probably not going to have shared memory. Isn't that fun?
Sorry, briefly, how does this differ from, for example, the cell architecture you would see with a PS3 that kind of bomb?
It works. It's vastly more parallel, and this is a route that you can see manufacturers pushing. So the cell architecture was basically very specialized processor architecture. It was essentially designed for the same kind of market as a graphics market. And GPUs, they're pretty successful. Okay? So in architecture terms, yeah, pretty similar. This is where we're going, driven by the imperative of energy versus performance, we predict. Probably not shared memory. So you can see this happening already. Intel has been dipping its toe in the water with things like hardware transactional memory. Assuming a shared memory hardware model is simply not going to work in the future. Uniform shared memory is not going to be there. Wait a minute. This reminds me of something. Wait a minute. What was it? Actors? Yeah, a bit like actors. Yeah. And there's a language that does things a bit like actors, right? It's oh yeah, Erlang. That's right. Yes, I remember that. And this Haskell thing. Didn't we do some in the past? These languages look like they could be the right kind of thing to fit the architectural models that we're pushing towards, because you're stepping away from very tight integration, shared, etc. You have a natural decomposition of objects into tasks. So let me tell you a bit about the fastest computer in the world today, just to show you that the megacore computer is not complete sci-fi. This one here is the second fastest computer in the world. It was the fastest for 3 years, which is pretty impressive. It's in China. It's the Tian-2 from the Chinese National University of Defense Technology. I wonder what they're doing with that. Please don't tell me. Very high performance, 33.86 petaflops. It has 16,000 nodes. Each of them has 2 Ivy Bridge multicores, so they're pretty juicy, even compared with current tech. Apple take note. And each of them has 3 Xeon Phis built in. So each of the nodes has 3 of those accelerators. That's going to be something like 200 cores plus the CPU cores per node of this device, linked up using a complex network. You can do the math, as they say in the US. If you do that, you realize you've got 3,120,000 cores. So megacore computers are not just the future, they're the present, if you're the state of China. And this one just took over in 2016, to show that things are getting even more exciting. This is the fastest computer in the world. Know where this one is? China. Good guess. Some way to highlight the National Supercomputing Center in Wuxi in China. 94 petaflops. It's about 3 times more powerful than the previous version. This one, interestingly, it has 40,000 nodes. Each of them has a chip with 256 Sunway cores in them. These are China's own CPU design. Okay? Very interesting device. You can look it up on Wikipedia, you'll find it. Again, if you do the math, 10 million cores in this device. Pretty impressive. And slightly more expensive than those Xeon Phis that I showed you. Megacore, I think. Or maybe mega hot, right? Because energy usage scales linearly with the number of cores, which is great, cubically with the clock frequency. And you can bet the clock frequency on these devices is going to be pretty high. It's not going to be the 1.5 gigahertz that we saw for the Xeon Phi. It's going to be 3 gigahertz, 4 gigahertz, etc. Huge power and energy usage. And this is critical for today's computers, as Samsung have discovered. It's not just about large systems, it's also about small ones. So even mobile phones are multi-core. Samsung has a device called Exynos 5 Octa. This has 8 cores in it. Pretty cool. At any point in time, they're only using 4 of them. Bit weird.
Let the others cool down.
Yeah, let the others cool down. Well, yeah. The others are monitoring the device to make sure it doesn't catch fire, perhaps. No, there are 4 big, fast, juicy cores, the equivalent of the x86, and there are 4 lightweight, low-performance cores, and the device can switch between them. So you can either have the big ones running or the small ones running. So if you're doing stuff like reading your email, calculating the spreadsheet, all that boring work stuff, use the small cores, and if you're running Angry Birds, you can use the big ones, right? So you've got a choice. And even embedded systems are becoming multi-core and heterogeneous. They would like to go faster, they would like to go bigger, but there are constraints on, for example, A, cost in the embedded space, and B, safety. Okay? You really have to worry about some of these devices. We need to solve the multi-core, many-core problem to make progress in almost all areas of computer science, almost all applications. I can confidently predict that all future programming is going to be parallel. It already is to a large extent. If you're doing big data, buzzword, it is about big data. Performance matters here. And the Internet of Things is going to produce humongous amounts of data which have to be processed very, very efficiently. How are you going to do that if you don't have big iron to do it? You cannot decompose all of the data and stripe it out along a lot of tiny cloud devices. You have to have some really serious processing power underpinning that. So this is going to push us towards more powerful computing devices. But doesn't that mean that you're going to have millions of threads running on a megacore machine? Well, yeah, of course you are. Here's a little application that I did earlier. What you'll probably see, the green is basically showing the application running. This application ran for about 5 seconds. I don't know if you can read the numbers down here, but I'll read them out for you. 33106 sorry, 3311615522. Okay? That's the number of threads this application created in 4.5 seconds. Fun, unless you've got the wrong system. How do we get that to work? This is not future tech. This is Haskell. What happened is we took those 331 million threads, which are potential work, and we transformed them using sophisticated runtime technology into 20,000 that did the real work. Still quite a lot of threads, but much more manageable on this device, which only had about 4 or 8 cores, than 331 million. And that's the secret. Have more parallelism than you need, and then you have ultimate scalability. You can run on small devices, phones, etc. You can run on big devices. Your application will still work. Okay? Portable scalability. So I'm going to digress, and I'm going to tell you how to build a wall. And this is with apologies to Ian Watson from the University of Manchester. I gave a talk there one time, and Ian said to me, yeah, this is all great, all these threads is great, but there are just some problems that you can't decompose, that you can't make into parallel problems. I said, well, yeah, okay, sounds good. Like what? Okay, I like a challenge. So Ian said, well, you can't build a wall in parallel, can you? You've got to put a brick and another brick, okay, and you've got a course of bricks laid out, and then you've got to put another set of bricks, right? And then the third row of bricks, and clearly, that is a sequential process. Yeah, you've got to do the first row, then the second row, then the third row. So I thought, well, let's imagine that we can employ 4 Polish builders whilst they're still allowed to build walls for us. How well could they do? Well, 4, we could place a number of bricks, yeah? And we could place some more bricks. And we could do the same. And we could do the same. And hey, it's parallel. It goes faster. How much faster? 4 times?
The number of processes?
That's 4, yeah. 4, yeah. Length of the wall. 6. Well, you can work it out. Placed 3. So 4's looking a bit dodgy already. And another 3. So it's looking very dodgy. 4. Okay, a bit better. And another 3. And another 3. And a final 3. So it's a bit more than 3. Even though we've got 4 processors, highly efficient, no synchronization, purely theoretical, we still can't get all of them working all at the same time. To do that, you need to have the excess amounts of parallelism that I described a few slides ago. Then you're cool. So there are fundamental limits. Even if you throw more cores at a problem, it ain't necessarily going to go faster if you can't break the problem down even further. Anyone see any better ways to do this? Well, I've seen people say you could prefab a complete row section, then all you have to do is lift it into place somehow and put it in. And then you get essentially infinite speed up. Stripe it, yeah. How are you going to stripe it? Yeah, build diagonally. Yeah, that's right, you could do that. Yeah, which is a very cool technique and one that people use when they can. Currently, people mostly program those things by hand. Okay? That's a bit tedious. Let me show you how not to build a wall. Place a brick, and another one, and another one, and so on. And we end up with our wall. Okay? Now, if there are any mathematicians in the audience, you'll see this is provably equivalent to the previous wall. It is functionally equivalent. But it's nonsense. Why is it nonsense? Gravity, yeah. I ignored fundamental dependencies. When I placed the first brick here, there was nothing to support it. And we know from real-world experience that when you put something down, you have to have the necessary supports. There are fundamental restrictions. However, the idea that you have to place the first row first, that's a completely arbitrary dependency. We thought we had to do that, but it wasn't really necessary. Breaking those unnecessary dependencies, but realizing that there may be necessary dependencies, is the foundation for getting good parallel performance. And that's what we want to try to do. Break as many dependencies as we can. So task identification, finding the bricks, is not the only problem. We also have to consider lots and lots of other issues to coordination, communication. The bricklayers have to talk to each other. If they don't, their fingers get trapped. We have to worry about where the bricks get placed, which one goes first. We have to worry about which bricklayer does their task first, etc., etc. Huge, complex coordination task. As the programmer, we should not have to deal with that. But if you're using a typical concurrency approach, today's programming languages, by and large, you are forced to solve these problems yourself by hand. And that is one of the reasons why we're still on 2 or 4 cores and not on hundreds or thousands at this point in time. We need structure, we need abstraction, we don't need a brick in the wall. One of our heroes, Bjarne Stridstrup. Multicore programming is too hard for developers today. Okay. It's a big challenge. How to get normal guys to do parallel programming. How to do parallel programming? Well, the solution, of course, is functional programming. So, according to Hopper, and you can verify this because it's on his Facebook page, the only thing that works for parallelism is functional programming. And I'm going to say, and patterns as well. So patterns and functional programming go together extremely well. Patterns are everywhere. The human brain is tuned to recognizing patterns in nature, in engineering, in all kinds of situations. We like patterns, they allow us to simplify problems. So let's try to exploit the idea of patterns. And they're already there in parallel software. Now, here are a few that you're probably familiar with. Everyone gets taught about pipelines in their university degree. Very few people probably program using pipelines. But a pipeline, what happens is we have a piece of code, we take some, do something, pass it on to the next pipeline stage, and so on. And if we have multiple processes, each of those cores could be executing a different pipeline stage, so you can get parallelism. Multiple things happening at the same time. Good, relatively boring. We can also do things like maps. You all know about functional programming, right? Yeah, good. So a map, we can take a data structure like a list, we can apply an operation over the data structure. So we apply the same operation to all the elements of the data structure. Hey, that's parallel. I can scale that almost as far as I like, certainly to the number of elements in the data structure, which could be millions. Okay? So bingo, good way to keep my megacore systems fed. Or I could use this pattern, a task farm. Now, it looks pretty much like a map. The difference is that with a task farm, the number of workers is going to be fixed. And what we're going to do is going to take the tasks and spread them out amongst the workers. So we don't just create one task per element of data structure. What we can do is we can have complicated workers working on different tasks as they come in and producing results not necessarily all at the same time, but as they become available. So that turns out to be an incredibly powerful mechanism if you're living in today's sadly rather restricted world where you only have a few cores, tens of cores, and you don't yet have your thousands or millions. Because then you can say, okay, what we're going to do is basically map some of the operations onto the cores that we have. These become our workers. Bingo, all works very nicely. And there are other nice things too, reduces, divide and conquers, etc., etc. So this is great. So let me show you a couple of implementations of those patterns. First one is how you implement a parallel task farm. Well, what we do is we've got a fixed number of workers all doing the same thing. We've got items, tasks coming in, and we split them up amongst the workers in some way. Each of these does its own thing, and at the end, out comes the stream of results where the worker has been applied to each of the incoming elements. Not necessarily in the same order. Functional correctness? Or pipeline. Take some input, process it, pass it on, do something, pass it on. And you'll notice that here I'm using some buffering just in case these pipeline stages are not running at exactly the same rate. There's a whole, you can write complete PhD theses on how to deal with the different rates between different pipeline stages. People do. So what are we going to do? What are we trying to do in the work that we've been investigating? Well, the idea is to produce a programming methodology which is going to be tool supported, where we start bottom up, identify components in the program, the bricks in the program, using refactoring tools. Think about the patterns of parallelism. So how can these components be structured together to build some pattern, which can then be collated to build the wall? Structure them into the parallel program, turning them into concrete skeletons or concrete task farms, pipelines, etc. So real code. And you probably want to take things like performance and energy, etc., into account at that stage. Go ahead.
So what do you mean by strongly hygienic in software?
Yeah, I wasn't going to go into that just yet. But code, the problem is that if you've got two pieces of code that interact, then that creates a dependency between one piece of code and the other. So very important when we were building the wall that the dependencies were all explicit. We could see when we placed this brick, there's a dependency between that and the one above it. If you have two components and they share a variable, that's pretty uncool. Because now you've got to work out what are the possible execution orders between these, because you can't simply plug them together in arbitrary orders. There's a dependency there. Okay? So when I say strongly hygienic, what I mean is the components shouldn't interact in ways that are not clear, because then I can't detect the dependencies. If you're a Scala programmer, do you have any C programmers? Maybe. But if you're a Scala programmer or someone who likes effects, I don't really care what happens inside the component, because nobody sees that. So side effects inside a component, who cares? Doesn't matter. It's the visible ones, the interactions, that are really important. Okay? So that's what I mean by strongly hygienic. Good. So components clearly take advantage of functional programming concepts. They provide clean abstraction, pure computations, which are easily scheduled, and expose the dependencies. This is what we were just saying. And you do need hygiene or discipline to make this work, because unwanted state leakage is going to kill you. Okay? Shared memory is going to kill you. So, how are we going to find these patterns? Well, you could just sit there and scratch your head for a while and hope they pop out. But we quite like developing tooling to do this. So it's Halloween. What we're going to do is use a process called anti-unification. This is going to frighten the type theorists no end. Basically what happens is we merge two bits of code. So we anti-unify two pieces of code. And the anti-unification creates the most general piece of code from those two parts. Okay? So the idea is you've got the code that I've that my programmer has written, I've got some pattern, some code representing a pattern. If I anti-unify them, what happens is I get a generalized version of the pattern that I can then instantiate however I want. Okay? So I don't have to pop in programmer-specified skeleton instances. I can do anti-unification, and it will tell me, hey, look, that thing over there, it's a map. That thing over there, hey, could be a pipeline. Pretty cool. Check out Adam Barwell's PhD thesis next year. So we're looking into the future here. Or talk to us. If you want to try this stuff out, please tell us. We very much like working with guinea pigs. So how does this work? Start with the original program. Start with the original function. This is part of a particle simulator, so it's the mass calculation. What it does is take a list of particles and works out the energy. It doesn't really matter what it does. I don't care. I'm a computer scientist. Bit of code. But that's what it looks like. So what we're doing is we're applying an operation over an empty list, and we get some value integer out, or we work over a list with a particle and some other particles, and we just add the mass for the particle into that, and we recurse. Okay? You all see what this is, do you? Yeah. Recognize the pattern yet? So what we have to do is to find the H, the anti-unifier, with some pattern. So what you can figure out is, well, H is a function, and what it does, it takes a function as an argument, something called init, and a list, and gives us back init. Or it takes a particle, and what it does is apply some function to M, and then recurse. It's a fold, yes, very good. Well spotted. It's a fold. See, you can do this stuff. You don't need the computer to do it for you. It's kind of handy. Unfortunately, the version I just created doesn't quite work. Okay? So I've got the right structure. Unfortunately, the types are a bit screwy. So actually, what I really need is this guy here, which is a pure fold. But in general, I might end up with something which is more general than fold. It might have more things than the fold. It might be more special. It might be specialized to the particular construct that I'm dealing with. And having got that, you can just rewrite it. Now I know H. I know, because I've picked the patterns to be specific patterns, I know I've got good parallel implementations for those, and I can also check all the side conditions. Is this thing hygienic, et cetera, et cetera. Okay? I've written it in Haskell, so of course it's hygienic. But if you're in one of these more primitive languages, well, yeah, you need to do some checking at that point. I'm trying to offend everybody.
Well, before you offend everyone, you put in a lambda like that. You are
Yeah.
in a logic of some flavor.
Possibly. Yeah, you're saying I'm steering arguments through that point. Yeah. The fault, but it's just a pattern. If I do it as you're describing, you think I'm going to fold like that, don't you?
That isn't continuation necessarily.
But it is just a pattern. It's not normally a very good parallel pattern. No. But a fold is a good parallel pattern. Even if I'm adding the lambda. No, even if I'm adding the lambda. Still a good parallel pattern. The reason I know it's a good parallel pattern is that's the way that GPUs work. I probably want to get on, but the technical details are there are properties that need to be applied to the operation, including associativity, and then you can use the left and right fold. So you're not restricted to just the right fold version. You can use the left or right fold. So the lambda isn't the problem, but it does have to have the right properties. Good. So how do I find the right pattern? Well, you can capture the parallel structure as a type, and there's a paper that we presented in October, that's last month, I guess now, in Japan, that tells you how to do that. So basically take your program, build some type, get a type for the structure, build a formal semantics and parallel cost model. Got a paper that we wrote last year, which has just been published, that tells you how to do that. And then use some type magic to automatically rewrite the source code. Okay? If you want to know what the type magic is, go and read our ICFP paper, but roughly speaking, it's the third homomorphism theory and category theory. Okay? So simple. All you have to do is understand category theory, and now you can rewrite parallel programs. Great. Or we could do it for you. So this is the idea. Start off with your initial program, discover patterns using anti-unification, build a structured parallel program, do some type inference on that to tell us what the parallel types are. From that, we can work out an operational semantics, and the operational semantics tells us what the costs are of executing each of the parallel structures. Okay. This then lets us define some transformations using the third homomorphism theorem, etc., that allow us to take one structured parallel program and turn it into another one. Okay. Once you've encoded these transformations, you can forget all about the category theory. They're just things that tell you when is it valid to do one transformation to another. And we can do that. We can have a type-driven system running our transformations and choosing different parallel structures under type control. Just change the type, and your program runs faster and does all the transformations for you. And then we spit out skeletons at the bottom. Neat. Little example, image merge. What image merge does, it takes a list of pairs of images and gives us back a merged one. Two operations of merge and a mark, so I'm using composition here, sequential composition. There are lots of implementations of that, including farming the entire thing, so where you've got a sequential execution of the merge and the mark. You could pipeline the mark with a farm. You could pipeline a farm on the merge with the mark. Lots and lots of alternative parallel implementations from this very simple definition. How do we choose one? Well, what we're going to do is decorate the function type with some information that tells us just what the type is as a structure. It's basically capture the code structure in the type. And now, using our cost model, we can use that to automatically select image merge 2, if that's the most efficient implementation. And if you want, you can leave holes in the types and let the system infer bits too. Okay, so you can infer bits of your types, all described in this ICFP paper, so please ask for a copy of that. We're using that to produce a refactoring tool. So the idea is going to build this into an IDE. We're currently working on Eclipse, but we're also looking at Visual Studio. And we're doing this for C, C++. Okay? I know it's not functional, but you saw what Bjarne Strostrup was saying. You know, those guys need our help, right? And who are we to stand back and let them suffer when we know all this cool stuff about hylomorphisms, etc.? Yeah. Yeah.
Do you have a way of kind of annotating stuff and saying, well, I really don't want
Yeah.
this reorder?
Yeah, this is a very good question. So the question is, when are you allowed to apply these operations? Now, if you're taking a purist view, then you can only do these when you have very strong mathematical properties. Okay? But most of us are computer scientists, and we kind of don't care if things are slightly wonky in various places. So depending on your application, you may have weaker conditions over what it means for two programs to be functionally equivalent. You notice, for example, that I was reordering tasks earlier. In a lot of applications, it doesn't really matter. You know, Googling, for example, doesn't matter which search gets done first. So by applying a temporally ordered requirement there, we're over-serializing. But if you do need to know those properties, what you need to do, in principle, is to use a theorem prover. Okay? Good theorem provers today include working out what the rules are and applying them automatically in your system using Idris, etc., etc. So there are good mechanized ways to deal with these properties, for some properties. Or you can put in checks. Say, well, we don't think this is good. If you still want to go ahead and transform it, you're the programmer, you're the boss. Live dangerously. We're not going to guarantee that you're still going to get the same result out. But hey, you're already living in that world because you have testing. Okay? I've got about 5 minutes left before I need to stop. I've got a video here. I can show you the tool in operation, or I can skip ahead. What do you want to do? Vote for the tool? A few of you? Yeah, most of you? Let's go and do that, and I'll skip over the next bit. So just show you this thing in operation. And I'm going to call on the services of my colleague in St Andrews, Chris Brown. By the power of the internet.
The ParaFormance tool on an application that generates this fractal image. And this is representative of the many calculations used in software from banking to automotive. The first step is to identify the opportunities for Multicore. After a few moments, these are displayed in green. We can then choose one of these and refactor it to enable it for Multicore. Before we proceed, however, a safety warning message is displayed indicating a potential problem. And this is typical of the type of problems software developers face when writing Multicore software. Assuming we are a typical software developer, however, when we think we know better, we are going to ignore this error for now and continue anyway. A preview pane is displayed showing the changes that the tool is going to make. And this allows us to run our application, getting a 3 times speed up over the original. But, shock horror, it gives us the incorrect result. And this is because we ignored the safety warning from before. So we revert our changes, and this allows us to rerun the safety check. Safety check tells us where in the program the error occurs, giving us more information in the problem pane below. We can then repair this using the menu item and refactor it to again enable it for Multicore. This time there are no safety warnings, and we rerun the application again 3 times faster, this time giving the correct result. Our ParaFormance tool is a compelling proposition because it enables software developers to write Multicore software in a matter of minutes as opposed to days or weeks. This brings products faster to market, saving companies time and money.
Thank you, Chris. Just go back to the presentation. So you've seen the tool, see that it's pretty easy to use, menu-driven, and helps identify the kind of problems that you might face in parallelizing code. We're applying this to some large-scale demonstrator applications, one of which is developing a cure for cancer. Okay, so we're really going to be saving people's lives using this technology. Pretty neat. And these applications are worth millions of euros, many millions of pounds. No good if you don't get speed up that's as good as you can do by hand. What you can see from this graph is the automated solutions are just about as good as the hand-produced ones. And in some cases, we're doing better than hand-produced code. But it takes a few hours using the tool rather than a few days, weeks, months of effort. And we know the code is right if you don't ignore our warnings. So to conclude, Manycore is here. Functional programming and patterns greatly add abstraction. We need software engineering to address parallelism intrinsically, and that's what we're trying to do through this ParaFormance tool and the EU project that I have. But I think a good take-home message is, hey, functional programming is mainstream. All these new versions of languages are including functional programming constructs, and that's going to let us do the kind of thing that I've just shown you in those languages. So tomorrow, C++, then Java, then the world. We're grateful to our funders, European Union, and to our partners, IBM, etc., who are putting this into real practice. I'm trying to commercialize this at this point in time. You'll notice that the video was basically a pitch. So we delivered that in May. We've secured £400,000 of funding to keep us going for the next year or so. We need you. Thank you very much.